Greetings to everyone from Spain. The purpose of this discourse is to provide a comprehensive overview of local anesthetics. While this subject matter may initially appear somewhat arid, it will be meticulously organized and presented in a comprehensible and fun manner to facilitate easier comprehension. In order to simplify and facilitate the understanding of the following information, some degree of embellishment may be employed. While the subsequent information may not be entirely accurate, its presentation will facilitate a more comprehensive understanding of the subject matter. Local anesthetics are a medication that causes the absence of all sensation in a specific body part without loss of consciousness. One of its main characteristics is that the effect produced is temporary, reversible, and acts specifically on the nerve fiber. When we inject a local anesthetic in the vicinity of a nerve conduction block will be produced. This block is characterized by its bidirectional nature, its temporary duration, its reversibility, and its specificity, as previously mentioned. This procedure is referred to as a nerve block. Local anesthetic drugs are water-soluble salts of lipid-soluble alkaloids. Each vial of local anesthetic contains millions of molecules, which we will refer to as anastases. Each of these molecules possesses a weak base characteristic, akin to the image of a basketball player with a basket in hand. The pKa range for these molecules falls between 7.5 and 9. The significance of this pKa will be explained in greater detail subsequently. Chemically, each of these molecules consists of an aromatic ring. It is fat-soluble and will therefore determine the intracellular diffusion and its binding to proteins, its potency. An intermediary link that gives the name to the family to which the local anesthetic belongs, ester or amide. Esters are metabolized in the liver and amides by plasma esterases, and an amine group, a tertiary amine hydrophilic, will determine the extracellular diffusion of the drug and its pK, and thus its latency. Lidocaine was first synthesized in 1946 and rapidly became used worldwide, given its superior safety profile compared to older local anesthetic agents. Lidocaine is a chemical compound that belongs to the amide class. As a result, it is metabolized in the liver. Its chemical structure consists of an aromatic benzene ring attached to an amide group and a side chain containing an amino group. Its pKa is 7.7, and it is one of the most widely used local anesthetics today. Like lidocaine, bupivacaine is an amino-amide anesthetic. Unlike lidocaine, the terminal amino portion of bupivacaine, as well as mepivacaine, ropivacaine, and levobupivacaine, is contained within a piperidine ring. Its liposolubility and pKa of 8.1 give it different characteristics from lidocaine. Chloroprocaine is an ester local anesthetic, commonly available in its salt form, chloroprocaine hydrochloride. Its primary characteristic is that, as it belongs to the ester group, its metabolism is plasmatic. Consequently, its average life is much lower than that of the local anesthetics of the amide group. Enantiomers are a type of stereoisomer that have the same molecular formula and sequence of bonded atoms, but differ in the way the atoms are arranged in space. They are mirror images of each other. Enantiomers have one or more chiral centers. The chiral center of bupivacaine is a carbon atom with an oxygen atom attached to its right hand. That's why we call it dextrobupivacaine. If we rotate dextrobupivacaine to the left side, we will obtain levobupivacaine. Its physiochemical characteristics are virtually identical to those of bupivacaine. The general conclusion is that the aromatic ring of local anesthetics allows them to be diluted in fat, enabling them to cross cell membranes and bind to proteins. The tertiary amine confers the property of being diluted in water, and therefore diffusing around the axons in the extracellular fluid. The intermediate linkage in these compounds is critical for their metabolism and consequently their elimination. The intermediate link is the component that determines the allocation of the local anesthetic to a particular family or another. In this case, the allocation is determined by the ester or amide family. Those in the ester family are considered more unstable drugs and are metabolized by plasma esterases, which release a series of free active metabolites that can cause allergies associated with these drugs. Conversely, amide family drugs exhibit enhanced stability, relying on hepatic metabolism and renal excretion. This metabolic pathway precludes the production of active free metabolites, thereby mitigating the risk of allergies. To ensure accurate drug classification, we can adhere to the nomenclature system that utilizes the number of bocals, I contained in each drug. Therefore, all esters contain only one I, while amines contain two. Upon the administration of any local anesthetic into a living organism by injection, a proportion of the drug will be present in an ionized form, constituting its active form. This ionized form is characterized by its non-lipophilic nature, which hinders its ability to traverse the cell membrane. Concurrently, a non-ionized form, representing the inactive state of the drug, will also be present. While the ionized form is the active form of the drug, it is non-lipophilic and therefore will not be able to cross cell membranes. Conversely, the non-active form, being the lipophilic part of the drug, will be the only one capable of crossing the phospholipid layer of the cell membrane of the axon. Assuming that local anesthetics are weak bases with a pKa between 7.5 and 9, the following discussion will explore the meaning of pKa. The pKa can be defined as the pH level at which the drug is present in equal proportions in both ionized and non-ionized forms. The higher the pKa, the greater the ionized fraction in the solution. Let's look at some practical examples. When using lidocaine, which has a pKa of 7.7 at a physiological pH of 7.4, it is important to consider that the anesthetic will be predominantly in ionic form, the non-lipophilic form. In the event, the pharmaceutical compound is administered by injection into an acidic medium with a pH of 6.9. There will be an increase in the predominance of the compound in ionized form. This increase will be progressive, resulting in a reduction of the latency and effectiveness of the compound. If bupivacaine, which possesses a pKa of 8.1, is utilized, it is reasonable to hypothesize that the ionic form of the drug will exceed that of other medications with lower pKs, such as lidocaine. This observation prompts the inference that the increased proportion of the ionic form may contribute to prolonged drug latency. In the event of a decline in the pH of the medium to 6.9, a negligible quantity of the pharmaceutical agent will be present in a non-ionic state, with the predominant form being the ionic state. This renders the agent unable to traverse the cell membrane, with very poor blocking in terms of latency and effectiveness. Let us now examine how the active and non-active forms of the drug function visually. When a local anesthetic with a theoretical pKa of 7.4 is injected into the extracellular space at a physiological pH of 7.4, half of the drug will be in its ionic form and the other half non-ionic. The ionic form, being non-lipophilic, will try to enter the cell but will not be able to do so, while the non-ionic form, lipophilic, will enter without difficulty. Once inside, the non-ionic form will ionize by binding to a hydrogen ion group, considering the intracellular medium's abundance of hydrogen ions. Any drug that has not yet entered the cell will bind to a series of proteins, including albumin and alpha-glycoprotein. These proteins have a high affinity for binding to the local anesthetic, buffering 90% of the extracellular molecules. Once bound to these proteins, the local anesthetic will pass into the systemic circulation. In the event of a decline in the pH of the medium, leading to acidification, a higher proportion of the drug will exist in a non-ionic form. Consequently, the drug will encounter greater resistance as it attempts to traverse the cell membrane. If the medium is alkaline, the opposite effect will occur. We will find more drugs in non-ionic form, and therefore there will be more drugs available to cross the cell membrane and perform their task. In the case of the amide family, the drug will enter the systemic circulation after being buffered by albumin and alpha-glycoproteins. It will then reach the liver, where various enzymes, the most well-known of which is cytochrome P450, will metabolize it in the first phase and eliminate it secondarily by the kidneys. The ester group, once bound to proteins, enters the systemic circulation. In this case, it does not need to reach the liver, since plasma esterases immediately metabolize it, breaking the local anesthetic molecule into different active compounds that are subsequently eliminated via the kidneys. This accelerated drug elimination mechanism is a key differentiating factor for this family, contributing to a significantly shorter half-life compared to amides, whose metabolism is more prolonged. To understand how these local anesthetics block the conduction of nerve impulses, we need to understand how it propagates through the axon. The neuron cell membrane, also known as the neuronal plasma membrane, is a complex and dynamic structure that plays a crucial role in the functioning of neurons. It is composed of a double layer of phospholipids that forms the basic structure with hydrophilic heads facing outward and hydrophobic tails facing inward. Proteins include ion channels, receptors, and transporters that help with signal transmission and substance movement. Cholesterol that provides stability and fluidity to the membrane. Glycolipids and glycoproteins are involved in cell recognition and communication. The resting potential of a neuron may be considered analogous to the standby energy of the cell. It is defined as the difference in electrical charge between the interior and exterior of the cell when the neuron is not transmitting signals. This charge difference is maintained by the distribution of ions across the cell membrane. The interior of the cell is rich in potassium ions, while the exterior in sodium. Consequently, at rest, the neuron's interior is more negative compared to the exterior. When a neuron is exposed to a sufficiently strong stimulus, the sodium channels in the axon membrane undergo a process of depolarization, allowing sodium ions to enter the cell. Concurrently, there is an efflux of potassium ions to the exterior of the cell, resulting in a transient increase in the internal positive charge of the axon and a concurrent decrease in the external negative charge. This phenomenon, known as a change in membrane polarity, occurs as a result of the membrane's response to the stimulus. The initiation of this process, initiated by depolarization in one section of the axon, results in the subsequent opening of sodium channels in the adjacent section. This sequence of events is repeated along the axon, leading to the propagation of the electrical impulse as a wave. Let's take a look at how local anesthetics work. As previously stated, the injection of local anesthetics in the vicinity of a nerve results in the presence of the drug in both ionized and non-ionized forms. The ionized portion is unable to traverse the cell membrane due to its non-lipophilic characteristics, while the non-ionized portion exhibits a higher propensity for membrane crossing. Once inside the cell, the non-ionic form of the drug will ionize by binding to a hydrogen ion group, becoming active. Upon ionization, the drug is capable of blocking the sodium and potassium channels. The blocking of these channels, in turn, impedes the movement of ions in both directions in the presence of any stimulus. Consequently, the membrane maintains its polarity, thereby preventing the propagation of the nerve impulse. What factors will condition the degree of nerve block? The pH of the medium in which the local anesthetic is injected will be a determining factor in its performance. In circumstances where the pH of the local anesthetic may be reduced, such as the administration of epinephrine or the presence of infection, the ionized form will predominate over the non-ionized form. Conversely, circumstances that could potentially alkalinize the medium, such as elevated temperature or the presence of bicarbonate, might result in a heightened abundance of the non-ionized form of the drug. Consequently, these two scenarios can result in alterations in the latency of the drug, either in a positive or a negative direction. The diameter of the fibers will also affect the rate of blockage. Sensitive myelinic C fibers are the first to block, followed by the progressively larger myelinic A beta and motor A alpha fibers. As previously discussed, the chemical structure of each local anesthetic influences the type of blockade produced by the drug on the nerve fiber. Variables such as latency, half-life, metabolism, and potency are contingent on the specific drug employed. The quantity of local anesthetic agent employed also exerts a discernible influence on the characteristics of the block, encompassing both its latency and duration. Let's now talk about the adverse effects. It seems evident that if these drugs act on neuronal sodium-potassium channels, they will have the same effect in those parts of the body where there are neurons with this type of channel. The brain contains the majority of neurons in the human body, and the toxic effect at this level is the first to appear. The cardiac conduction system could also be affected, producing changes in the cardiac rhythm by the same mechanism. Methemoglobinemia is a condition where hemoglobin is altered, making it unable to carry oxygen effectively. This can happen with local anesthetics due to the oxidation of hemoglobin. Some local anesthetics like benzocaine, lidocaine, and prilocaine can oxidize the iron in hemoglobin from its ferrous state to a ferric state, forming methemoglobin. Methemoglobin cannot bind oxygen, leading to reduced oxygen delivery to tissues. High doses or prolonged application of local anesthetics increases the risk, and some individuals have genetic conditions that make them more susceptible. Symptoms of methemoglobinemia include cyanosis, headache, fatigue, and in severe cases, respiratory distress and altered mental status. Treatment typically involves stopping the offending agent and administering methylene blue, which helps convert methemoglobin back to hemoglobin. Ester group anesthetics are rapidly metabolized in plasma by the enzyme pseudocholinesterase, producing a compound called para-aminobenzoic acid, PABA. PABA is a known allergen that can trigger allergic reactions in some people. This presentation has facilitated a more profound comprehension of local anesthetics and their mechanisms of action. It is my sincere hope that it has proven to be as beneficial for you as it was for me during the editing process. Thank you very much for your attention.